another type of error recovery strategy is by means of error production. So, error production says that the language designer has given us a set of production rules that tells how the valid statements of the language can be designed, can be generated. Now, compiler designer can think about the possible errors that the user can do and accordingly add some few more productions into the system, which will be called error productions. So, if a particular going back to that example that we are taking of if then else statement, so it is so it was like this, the S producing if some condition, then statement, else statement. Now, this is a rule from the language, this is a production rule from the language. Now, compiler designer can interpret or can try guess that the type of error, type of mistakes that the user can do is forgetting this then. So, accordingly the compiler designer can add another rule to this language. So, if C S else S, then what will happen if a program has got a line where we have got this where the then part is missing, then what will happen is that this rule will not match, but this rule will match. But the compiler designer knows that this is a error production. So, it should not try to generate code based on this, but the parser it will be able to proceed with this rule and it will not fall into an error condition. So, that is basically used in the error recovery of the parser. So, this is the error productions. So, we can augment the grammar with productions that generate the erroneous constructs. So, this is the other possibility. And also we can do some global correction. So, we can find out some minimal sequence of changes to obtain a globally least cost correction. So, this is a very I should say costly approach. So, what it is trying to do is that there is an input program. So, there is an input program say P and it has got some errors in it. So, what it will try to do is to transform this P into another program P dash, where all those errors have been corrected and that correction is global. So, for example, if you have got say in your program, suppose you are using a variable x and at various places in the program. So, you are writing like x equal to y plus z, p equal to x into k, like that, and if this variable x is undefined, then you see that at every place it will generate a message that x is undefined, like that. So, you can transform this program into another program where at the beginning you guess what is the type of x, since I am doing this addition and multiplication integer operation. So, I can define x as integer. Okay. So, this line may be introduced into the program, rest of the thing remains as it is, only this extra line has been introduced. So, what will happen? This program will not generate any semantic error. So, that way the parser will be able to proceed, the compilation process will be able to proceed, or say so x will get installed into the symbol table. As a result, it will, the lexical analyzer will be able to return proper token that x is an identifier token. So, like that. So, it will help in the compilation process. But there can be many ways, there can be many interpretations. So, why do not we replace x by a constant number? So, that is also a correction, but so that way what is the minimal number of changes that can be done in the program to obtain a globally least cost correction. So, that is the challenge of this global correction strategy. So, this is particularly useful where we have got text formatting type of application, where we try to show the output to be as correct as possible to the user, and if the user is not satisfied with the output, we will perhaps go to the correction. But many times what happens is that the correction done by the formatting tool is good enough and we do not do any further corrections. So, this global correction has got applications in text formatting type of cases. So, next we will be looking into in more detail the grammar. So, this is coming back to the context free grammars. So, as I was telling that most of the programming languages, so they have got this context free grammars, they can be specified in using context free grammars, and as I said that it has got 4 sets in it: terminals, non terminals, a special start symbol which is a member of the set of non terminals, and the set of production rules. So, this is a typical example of a grammar. So, this is known as expression grammar. So, throughout our course many times we will be referring to this particular grammar. So, we read it like this: expression produces expression plus term, then or expression produces expression minus term, or expression produces term. So, term is basically product of two sub expressions, okay, and an expression can be sum of two sub expressions, or the sum or the subtraction of two sub expression, or it may not have any such addition subtraction. So, if it is say and only product, so 2 into 3, in that case this whole expression is considered as a term using the third rule, and then this term is taken as it is taken, a term is can be term multiplied by factor, or term divided by factor, or a term can be simply a factor, and factor can be within bracket expression or a single identifier. So, this way we have seen previously some derivation. So, this is a grammar, and we will be calling this as expression grammar, and it takes care of expressions, arithmetic expressions having the operators like plus, minus, multiplication, division, and the parenthesis. So, it takes it can detect parenthesized expressions involving identifiers and the arithmetic operators plus, minus, multiplication, star and slash, addition, subtraction, multiplication and division. So, this is a good example, and very often we will be referring to this example. So, derivation. So, we have already seen something called something like derivation, like see, suppose we have got an expression like this, a grammar like this. So, it has got a set of rules, E producing E plus E, or E star E, or minus E, or within bracket E, or I D, fine. So, this is the grammar. So, we can have a derivation for this one. Say suppose this is the expression given to us, minus I D plus I D. So, how can we derive it? So, we can do it like this. First we apply this rule, E producing minus E, so that this unary minus is taken care of. Then this E is replaced by within bracket E. So, this open parenthesis close parenthesis parts have been generated. Then this E is replaced by E plus E, okay. So, because I need to generate this I D plus I D, then this first E is replaced by I D, and in the next case the second E is replaced by I D. Okay. So, this is one possible derivation of the string minus of I D plus I D, starting with the start symbol of the grammar E. Now, somebody may say that I have a choice at this point. So, when I am looking into this E plus E, I have a choice whether I can replace this E by I D, or I can replace this E by I D. In the first case, we have replaced the first E by I D. So, there can be another derivation where the second E is replaced by I D first, and in the next derivation the first E is replaced by I D. So, in general I can say that if I have got a string, okay, so I have started with the start symbol of the grammar, and from there I am deriving the strings like this, then at any point of time, suppose I have got some string like I D plus E star E plus I D like this plus E. From this I want to generate my next string. Okay. Now, there are possibilities like I can replace this E, I can replace this E, or I can replace this E. I have got 3 choices. Now, there are 2 derivations that have been that is followed into by the compiler designers. One is that you replace the leftmost non terminals, that is this one. So, that is known as leftmost derivation. So, in the next derivation, so if I write it like I D plus this E producing I D, star E, etcetera, etcetera. So, that will be a leftmost derivation, because I have replaced the leftmost non-terminal by the right hand side of the corresponding production rule. Or I can replace this E. Okay. So, I can have the derivation like E star E plus I D plus this E producing, say, within bracket E, that can be done. So, I have replaced the last E, the rightmost E in this case. So, we can have two different derivations, one is called a leftmost derivation, another is called a rightmost derivation. So, in the rightmost derivation, from the intermediary string, the rightmost non-terminal symbol is replaced by the corresponding right hand side of the production rule, and in the leftmost derivation, the leftmost non-terminal is replaced by the right hand side of the corresponding production rule. So, this is known as derivation. So, productions are treated as rewriting rules to generate a string. So, they are basically productions are nothing but rewriting rules. So, we can replace one string by another string by applying those rules, and there are derivations like rightmost derivation and leftmost derivation. We can think about a parse tree like the derivation that I have done in the last slide. So, you can think of it to be like this. So, E is the start symbol of the grammar, and from there we have got E is the start symbol of the grammar, and then I have replaced the rule E, I have used the rule E producing minus E. So, minus, so it has got two children nodes, one is the minus, the terminal symbol minus, another is the terminal symbol E, and the next step this E is replaced by within bracket E. So, so the derivation that we had is minus within bracket E. So, this E is replaced by within bracket E. So, that is the next part of the tree. Now, from this I can have this E producing E plus E. So, this E is replaced by E plus E. So, that is a next phase of this tree that we have, next level of the tree E plus E, and the next level this E produces I D and this E produces I D. So, this way I can have a tree representation of the derivation, where the first derivation that I have done. So, it constitutes the first part of this tree, and the root of this tree is the start symbol of the grammar, and from there the rules that I am applying. So, based on that we can have different branches in the tree. So, this is the parse tree type structure. Next, we will have sometimes so there can be ambiguities in a grammar. For example, suppose we consider this particular specific statement or example I D plus I D star I D. Now, I am following the grammar. I have got a simple grammar like E producing E plus E or E star E or I D. Since I do not have parenthesis and all in this particular string, so I do not need to consider the other constructs that the grammar may have, other rules that the grammar may have. So, we have got only these rules. So, one derivation for this I D plus I D star I D may be like this. We start with E, then replace it with E plus E, then the first E is replaced by I D, second E is replaced by E star E, and then this E is replaced by I D and this E is replaced by I D. Okay. So, this is one particular tree. Another parse tree can be like this. So, here I first replace this thing by E star E. So, instead of doing it like this, so in plus, so I am starting with this star. So, E producing E star E, and then this E it gives me E plus E, and this E gives me I D, this E gives me I D, and we have got. So, the derivation sequence in this case is E giving E plus E, from there giving I D plus E, from there id plus E star E, from there id plus id star id, so id plus id star E, and this giving id star id. And in this case what has happened, I have started with E, and from there I have got E star E, from there I have got this E replaced by E plus E, and then star id, okay, star E. So, let us do it like that. It is then this E is replaced by id plus E star E, then this is giving me id plus id star E, and that will give us id plus id star id. So, in both the cases I have got the final string id plus id star id, in both the cases, and both of them are doing leftmost derivations. Okay. So, here also I am substituting the leftmost non-terminal first in the substring. So, here also I am doing the same thing. So, if I do that, but even so both of them are parse trees corresponding to leftmost derivations. But even if I do that, you see that we have got two distinct parse trees for the same strings of the language. Now, which one is correct? Okay. So, sometimes, so whenever you have got more than one such derivations, so we say that the grammar is ambiguous in nature, because it has got more than one interpretation of the same string. In fact, if you look into it more carefully, then in this case you see that here this if you go in a bottom up fashion, then this id, so this id is replaced by E, and then E star E is replaced by E. So, you can understand that this expression multiplications is done first and then it is added to the first id. Whereas, in this case this id plus id, so they will be there. So, this thing, so ultimately this E plus E is done first. So, addition will be done first and then the result will be multiplied by the this E plus E is giving E. So, as if this addition is done first and then it is multiplied by the second E. So, which is if we consider the precedence of this addition and multiplication. So, multiplication has got higher precedence than addition. So, naturally this is not a valid interpretation of the statement, but as long as the precedences are not mentioned, so both of them are correct. Okay. So, the language designers they have to tell the precedence, and as a compiler designer either you have to design the grammar such that these ambiguities are not there. Okay. You can see shortly, like if I have got that ETF grammar where I have got the production rules like E producing E plus T or T, then T producing T star F or F, and F producing ID or within bracket E. So, this particular grammar, so this is known as ETF grammar. ETF grammar. So, this ETF grammar does not have this ambiguity. ETF grammar does not have any ambiguity because it says that for applying this rule, first this T has to be derived. So, this E plus T, so and the T will take care of this multiplication first. So, addition cannot be done earlier than the multiplication. So, this will be more clear when we go to the code generation chapter, but this we can just take a view that this ETF grammar cannot be ambiguous, and in fact, you will not be able to derive this parse tree using ETF grammar. For example, if you use ETF grammar, then you will always always have to do it like this: E plus T, then this E giving T giving F giving ID, and then this T giving T star F, and this giving F, and this giving ID, and this f giving id. So, this is the only parse tree that you can have. So, you cannot have any other parse tree for this ETF grammar, the leftmost derivation. So, it does not have any ambiguity, whereas this particular grammar where this T and F non terminals are not there. So, they are known as E grammar or expression grammar, and this is ambiguous. But many times this ambiguity is kept because in this case I have 3 non terminal symbols needed for writing the grammar E, T and F, and here there is a single non terminal, and we will see that the size of the parser. So, it will vary, it will be more if there are more number of non terminals. So, though ambiguity is difficult, but it is a problem for this parsing process. So, many a times we will allow this ambiguity, so that the size of the parser is less compared to the situation where you have got a totally unambiguous grammar. So, we will see as we proceed through this chapter in successive portions of this course. So, this is another source of ambiguity, like say this if then else statement. So, suppose we have got this statement, if this rule, like it says that a statement is like this, that if E1 then if E2 then S1 else S2. Okay. So, the corresponding grammar is this one. So, it says that a statement can produce if expression then statement, or if expression then statement else statement, or other statement. So, this is this other, actually it encompasses all other statements that may be there. So, we are not bothered about other statements. So, we have just kept it as other. Now, suppose we have got this thing, that if E1 then if E2 then S1 else S2. Now, so this one can be derived like this. So, this if E1, so this is the expression. So, it follows the first rule, if expression then statement, then the expression will be giving me E1, and this statement is again broken down into if expression then statement else statement, where this second expression part. So, this corresponds to this E2, and this S1 and S2. So, they are corresponding to then part and else part. So, another possible derivation of the same thing can be like this. Say I start with statement. Now, if expression, so I take the second rule. So, for the first level of derivation I take the second rule, and it derives like statement producing if expression then statement else statement, and for this expression gives me E1, that is fine. Now, this statement gives me this part if E2 then S1. So, this part. So, it does it produces like if expression then statement and E2 and S1, fine. So, this is the situation. So, what has happened is that in this case, in the first case, this in the first case, this else S2 part, this else S2 part is the confusion. Okay. So, in the first case in this diagram, so this has been taken with this particular if statement, as you see, if E2 then S1 else S2, whereas in this case this S2, the else part has been taken with the outer if. Okay. So, it is it has been taken like this, that as if I have got this whole thing as the then part. Okay. If E1 then this statement else S2. So, if E1 is false, it will go to S2, whereas in this case if E1 is false, it will go to the next statement, and if E1 is true, then it will come to check E2, and then it accordingly it will go to S1 or S2. So, there is the two different derivations are possible for the same statement. Whenever you have got this type of nested else, we have got this particular problem. What about this case, like if E1 then S1 else, if S2 then S2, if E2 then S2 else S3. So, here I have got in the then part I have got E1 and S1 else, and in the second part I have got if E2 then S2 else S3. So, here I do not have any confusion, because there was no, so here the problem occurred because one of the if statement has the else part, the other one does not have any else part. So, in the nested if, where does this else go? So, that is the ambiguity, that is the problem. So, in one case, in the first case we have taken else with the innermost if, in the second case here, so we have taken else with the outermost if. But if there are two such else's, so both the statements are if condition then statement else statement and nested like that, then there is of course no problem. So, this is always fine. So, there is no confusion here, but this is the confusion. And you remember that most of the programming languages, they will tell that this else is always attached to the innermost if. So, this is known as the problem of dangling else. This is known as the problem of dangling else. So, the most of the programming languages which allows this type of nested if then else statement, it will tell that if it is mentioned, if it is written simply like this, then this else S2 is always part of the innermost if. So, it is actually like this. So, the statement to be taken as if U1 then this whole thing. So, this is valid, but this is not valid. Okay. But as far as the grammar is concerned, both of them are valid. Okay. So, we have to do something to the grammar, so that it is taken care of. So, we do not have the problem of this type of dangling else. So, otherwise the parser will find a confusion here, and there are several ways by which it will report it, and as we proceed through the portion, you will see that there are different ways in which this will be reported by the parser. So, next we will be looking into how to eliminate this dangling else problem. So, one possibility is that a statement appearing between a then and an else must be a matched statement. So, this is the thing that we say that there are two types of statements, one is called a matched statement, another is called an unmatched statement or open statement. So, and a matched statement, so it can give me all other statements of the programming language, but as for when it comes to the if part, when it comes to the if part, then it is always if then else. So, I do not have the if expression then statement as the producible from the matched statement. So, if expression then statement can be produced only by the open statement. Open statement can also produce if expression then statement else statement, but this first then it must be a matched statement, and so that this else becomes a part of this. If the else is there, then it will become a part of this. If it is not there, so it will be a matched statement, so that if there is an else inside, so it will be matching with the innermost if. So, that way this solves this dangling else problem. Now, so if we do some derivation, then so this in the previous diagram, what will happen is that, so this part can be produced only by a matched statement. So, as a result, I cannot have this type of structure. So, only this structure will be possible, because this will be a matched statement, this is open statement and this is a matched statement, and the matched statement will have the else part with it. As a result, it will not be able to derive the first string. Okay. So, next we will be looking into some work that talks about eliminating the left recursion. So, many a time a grammar has got rules such that starting with a non-terminal, you can derive a string which is which is having again that non-terminal as the leftmost symbol. For example, if I have a grammar rule like this, say S producing say A, and there is a rule A which says that it can give me S B. Then what will happen if you apply these rules, then this gives me A, and from this A is again replaced by S. So, S B A. So, what is happening? so starting with A, you are producing this whole thing is alpha. So, alpha is a string of terminals and non-terminals. So, the first character, sorry, this is not alpha. So, alpha is this part. So, this is giving me S B A. So, this B A part is alpha. So, as per this convention, A producing A alpha. So, this S is giving me S alpha. So, that way the symbol, the non-terminal symbol that is there on the left hand side is appearing again as the first symbol in the right hand side. So, as if in some sense you can understand this is some type of recursion, okay, that is the same non-terminal symbol appearing as the first symbol on the right hand side. So, this the parsing methods that we have, so parsing methods cannot handle this type of left recursive grammars, because the top down parsing methods, what they will do, it will start with S and it will try to derive a string from here, say after some time it comes to the situation where it is S B A. So, basically it is back to this S. So, now again, so it will fall into a loop here and it will try to do that again, it will try to again apply the same set of rules to replace S, and that way it falls into an infinite loop. So, if you are looking for top down parsing strategies, then this left recursion is a problem. So, there can be some modification, simple modification to the grammar that can convert a left recursive grammar to a non left recursive grammar. So, the rule is like this. Suppose we have got a rule like this, A producing A alpha or beta, where alpha beta are strings of terminals and non terminals. So, we can replace it by A producing beta A dash and A dash producing alpha A dash or epsilon. So, you see that whatever strings that can be derived from the first grammar, that is this rule, can also be derived from this rule. Like here, so you can see that A can produce, so all the strings that this A can produce. So, A can be applying, it can go on producing A alpha. So, it can do it like this, A alpha alpha, A alpha alpha alpha. So, like that. So, it can do it like this, and ultimately this alpha has to be replaced by beta. So, it will finally give a string which is beta, then alpha alpha whatever. So, you see that using the second rule also, so we can do like this. So, we start with A, first we do beta, then A dash, and this A dash can give me beta alpha A dash, and then again this A dash can give me beta alpha alpha A dash. So, I just go on applying this rule, and finally, this A dash can be replaced by this epsilon. So, that you have got the beta alpha 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 like that. Okay. So, whatever string is derivable from this rule is also derivable from this set of rules, but the advantage that we have is the second set of rules, it does not have any left recursion in it. Okay. Unlike the first rule where there was a left recursion, the same non terminal was appearing as the first symbol on the right hand side. So, it does not happen in this case. So, here it is simply that situation does not occur. So, the top down parser, it can take a decision whether it should follow rule number 1 or rule number 2, that is whether to follow this rule or this rule for A dash. So, it will see that if the remaining part of the string it starts with alpha, then it will follow this rule. If it finds that it is the end of the string, then it will apply the second rule, A dash producing epsilon, to resolve the issue. So, that way the top down parser will not get stuck at that point, it will be able to progress. So, this way this left recursion elimination is a very fundamental step whenever we are going to discuss about top down parsing strategy. So, this is going to be one of the most important thing that we should do. We should scan through the grammar and find out where these left recursions are there, and we eliminate all those left recursions from the grammar.